Hi, my name is Angel Ramos, and my presentation today is on theoretical density. We start by defining theoretical density. Theoretical density is the maximum achievable density of a particular element, compound, or alloy. Here we have the theoretical density equation. The theoretical density is equal to the mass of the atoms in a unit cell divided by the total volume of a unit cell. The mass of atoms in a unit cell is equal to the number of atoms per unit cell multiplied by the atomic weight. The total volume of a unit cell is equal to the volume of a unit cell multiplied by Avogadro's number. In the next slides, I will be talking about the cubic structures and the different kinds there are, so we can evaluate how the number of atoms per unit cell changes with each one. And also, I will be talking about how the volume per unit cell, which is A cubed, will change for each one. The first cubic structure I want to talk about is simple cubic structure, which abbreviates to SC. SC has low pack density and is very rare, as only polonium has this structure. Simple cubic structures only have one atom per unit cell. Because there's 8 corners, each corner makes up 1/8 of an atom, so 8 times 1/8 is equal to 1 atom. The second structure I want to talk about is a body-centered cubic structure, which has the abbreviations BCC. The atoms touch each other along the cube's diagonals, and it has 2 atoms per unit cell. We see that it closely resembles a simple cubic structure, but it simply has an atom in the center. It has 2 atoms per unit cell, because again, as the simple cubic structure, it has 8 corners which make up 1/8 of an atom. So you have 1 atom, and in the center is another atom that equals 2 atoms per unit cell. The last cubic structure I want to talk about is the face-centered cubic structure, which abbreviates to FCC. Here the atoms touch each other along the cube's face diagonals, meaning there's an atom in between each side. So 6 faces, 6 atoms in between. Here we have 4 atoms per unit cell, because again, like all the others, there's 8 corners, making 1/8 of an atom, so together they make 1 atom. But now we have 6 faces with an atom and half an atom. So we multiply 6 by 1/2 and we get 3 atoms. So 3 plus 1 is 4 atoms in total. This one's a little bit more complicated to see. So if we remember the equation from theoretical density slide, we know that the volumetric of a unit cell is equal to A cubed. And we get this A value by imagining that this model is as packed as closely as it can, and remembering that each corner is 1/8 of an atom. We would get this image, which results in A being equal to 2 times the radius. Again, if we imagine this cubic structure to be as packed as closely as it could be, it would actually be different from the simple structure just because there's an atom in the center. Since there's an atom in the center, it gives us this image here, and we can see that if we draw a triangle for going from the top corner to the furthest bottom corner, we would get a triangle that has sides of A and square root of 2A, so our diagonal would equal square root of 3A, and we can see that the diagonal line goes across 4 radiuses, so we could equal 4R is equal to square root of 3A, meaning our A is equal to 4R divided by square root of 3. So here, if this model was collapsed as closely as it could be, it would again be different from each of the other ones just because there's more atoms involved. This one is a bit simpler, as we can just look at a certain face. We do a diagonal across the face itself, draw a line, form a triangle, so we know both sides are a, and the diagonal should be equal to square root of 2a. And as we can see again, it's going across 4 radiuses. So here we have square root of 2 of a is equal to 4r. So our a would be equal to 4r divided by square root of 2, which is again different from the other cubic structures. To show how theoretical density changes when changing a cubic structure, I chose a class problem which states iron has a BCC crystal structure, an atomic radius of 0.124 nanometers, and an atomic weight of 55.85 grams per mole. Compare the theoretical density to the actual density. For the solution, I used an Excel sheet, and I used every cubic structure to see how theoretical density changes. And as you can see, obviously the BCC is closest to it because that's iron's actual structure. The other ones differ because the numbers of atoms per unit cell changes, as well as the volume per unit cell changes of each one. And that's because the A value is different for each one. And so here we can see that we could actually work backwards. So if we didn't actually get the cubic structure of the element, we could check the theoretical density and see which one matches closely to the actual density to find out the cubic structure of that element. To conclude this presentation, the cubic structure chosen affects the theoretical density, and this can be manipulated to find out cubic structures of elements if the theoretical density is compared to actual density, just as I did in the previous example.